Now let's talk about sampling. So as we saw earlier when we discussed types of signals, many real-world signals have continuous values. In many cases, that's not only in terms of the time component, but also the amplitude. Now, if I want to get that signal and store it, I run into a problem, because when we have continuous values, that means technically between any two different values, there's an infinite number of values. So not only can I not capture an infinite number of values, but I also can't store an infinite number of values. That means then that we have to start taking samples, and we have to consider, well, how many samples to take. There's a trade-off here. If I sample too little, then I don't get enough information to reconstruct the original signal. On the other hand, if I sample too much, well, then I have potentially too many numbers to process, or it may take too long to process those numbers in a given time period. So let's look at this example. So here I have a cosine wave, and what's the frequency of this? Well, I'm starting here, and if we look here, this is time, so this is 1 second. So I start here, and there's a cycle, there's a second cycle, this is where a third cycle would be. So technically this is the first cycle, second, this is a third cycle, so the fourth cycle actually would be here. So this is 3 cycles per second, so it's a 3 hertz wave. And I'm taking samples right here and right here, because I'm taking 2 samples in 1 second. Now if I just gave you the 2 blue dots, what is the likelihood that you would reconstruct a 3 hertz sine wave here? Well, I would guess it's not very high, because if I continue to give you more samples, but it's only at 2 samples per second, well then the third sample would be here, we'd have a fourth here, whatever. Well, if you tried to connect those dots using, the shortest path, you go from here to here to here, well, it looks like it's really 1 cycle per second. So now I'm going to double the number of samples in 1 second. So here to here to here to here. Well, that's better, but it might not be good enough. So I'm going to double again to 8 samples per second. This is starting to look a lot better, but if I double to 16 samples per second, this is even better, because if I connect the blue dots, well, yeah, it's easy to see this looks like 3 cycles per second. So this is obviously the best, but is that really what we need to do? Well, eventually we'll find out this is actually more than we need, but clearly this is too little. So we have to find some sweet spot between the two. So now we're talking about sampling. We need to discuss frequency and period again. Remember that the frequency of a signal, like we had here, the frequency was the number of cycles per second, and the period was the length of 1 cycle. So here the frequency was 3 hertz, and so the period will be 1 over 3, which is 1/3 of a second. Now that we're discussing sampling, we find out there's also a sampling frequency and a sampling period. The sampling frequency, f sub s, is the number of samples in a second. And the sampling period is the distance between samples, and it's the inverse of the sampling frequency. So if I had 5 samples per second, then there would be 0.2 seconds between the samples, or 0.2 seconds per sample, if we're looking at it this way. So let's compare again, make sure we're clear. F is the cyclic frequency, and it means cycles in a second, and that's also the unit, although we typically just say hertz. T is the length of 1 cycle, and that's the cycle period, and because T is the inverse of F, the units are the inverse of these units, so it's seconds per cycle. F of S now is the sampling frequency, which is the number of samples in a second, and that's the unit, but this also is commonly referred to as hertz. So you have to pay attention to your situation to know, are we talking about cycles in a second or samples per second? And then the sampling period is the distance between samples. It's the inverse of F of S, so its units are also the inverse of this, so it's seconds per sample. So let's look at an example. So here we look at the time, it's 1 second, and so how many cycles do we have? 1 cycle, 2 cycles, so it's 2 cycles per second. What's the length of 1 cycle? That'd be capital T, the period. So that's half a second. Yep, that matches up. F of S is 8 samples per second. There's 1, 2, 3, 4, 5, 6, 7, 8. Because we started at time 0, then the next set of samples would start here, but we don't count that as part of this set of cycles, but it's 8 samples per second. And now the sampling period is 1 over 8, which is 0.125 seconds. So from here to here, does that look like it's 0.125? Yeah, it could be. It's hard to say. It's easier to look here and say, well, this is at 0.5. And so the first 4 samples used up half a second. And so that matches up. So how do we get from this continuous signal, the blue line, to our set of samples that are supposed to represent that line? Well, if this is our continuous time sinusoid, and remember I'm using parentheses and the letter T here to represent continuous time, well, if I had this right here and I wanted to take a particular sample, I could plug in a particular time and that would give me the value at that point in time. But now we see that given a sampling period T sub S, the way we find the samples themselves is we're going to produce a sequence here, X sub n, and I'm using square brackets here to make it more clear we're talking about discrete time. We'll take one of these integers, and they can be negative, and multiply by the sampling period. So 0 times T sub S would be 0, so this would be at time 0. Going back to this right here would give me this sample. And then if I plug in 0.125 here for T sub S, and I use 1 times that would be the time 0.125. What is X at that point? Once again, if we were using this particular signal, that would give me this. 2 times that would give me 0.25. That would be right here. 3 times that. So 0 times T sub S, 1 times T sub S, 2 times T sub S, 3 times T sub S, 4 times T sub S, and so forth. That's how I generate my sequence of sample values, because that's what X sub n will be as a sequence. Now, one thing to note, even though we won't be discussing it more, is that the hardware that does this for you is called an analog to digital converter, typically written A/D. And it would take the samples for you and spit those out. So a continuous time signal comes in, a sequence of discrete time values would come out. So this is what I was just discussing. And so if we did this, if we had this signal here, and I was sampling at 8 samples per second, the first 4 values, we would actually have more, and it would keep going as long as we wanted to capture values. But the first 4 then would be 0, 1, 0, minus 1. Now when I write X sub n like this, where I'm using the letter of n, we're talking about the sequence itself. But if I want a particular value in the sequence, then I replace n by one of those integers, where n is my index for a particular value. Now, when we program, our programming language will have its own particular method for indices. If you're using Python, the first value in the list has index 0. If you're programming in the C programming language, the first index into the array is also 0. If you're using MATLAB, the first index will be 1. It depends on your programming language. But when we're talking about digital signal processing theory, we're not actually limited to positive or non-negative indices. We actually can even have negative indices, and we will see that as we progress during the course. Now, for most of the examples I will do, we will assume that the first number here in our sequence has an index of 0. And so if we use that here, that means that X sub 0 is 0, X sub 1 is 1, X sub 2 is 0 again, and X sub 3 has a value of minus 1. All right? So that's sampling. What we'll discuss in another video is aliasing, and we also will discuss how many samples to produce, because going back to this example here, we said that we can easily see that 2 samples per second for a 3 Hertz wave, or cosine wave here, is not sufficient to reconstruct the wave, and 16 is too much. We'll see there's a formula that allows us to determine what the minimum number of samples are to reconstruct a signal.